Hello and welcome to the podcast According to Sci-Faith, in which we will discuss topics about science and faith and whether they are compatible to one another. If you are a regular listener to this podcast, then you know that there's also a book on this topic out there from me, but currently it does only exist in German. But there are some good news because currently I'm translating the book into English with the help of AI techniques. So I hope I can publish this book in the coming October, and then there will be also an English version available. There's also some part that is already translated into English, so I thought for today's episode, just to give you a small soundbite, a small taste of what this book is about, I will talk about it, and I will not only talk about it, but I will give you a really first insight into the content of the book by giving you an audio sample of the first chapters of this book, and I really hope you enjoy it. Chapter 1: Evolution of Theories. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing in the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. Sir Isaac Newton. To answer the question of the nature of theories, let's first be clear about what we are trying to accomplish in science in the first place. To do this, let's take a bit of a swing and look at the beginnings of science today. The beginning of modern science. According to legend, before Newton established his 3 axioms, he was lying under a tree when he saw an apple fall to the ground. This raised the question in his mind why this apple flew downward and not in another direction. In other words, what force moved the apple and all the other objects to fall to the ground or stay there? Obviously, Newton did not let go of this question, and he established 3 axioms to describe these forces, which are known today as Newton's 3 axioms. Now, what is an axiom? An axiom is something like the starting point of the theory. It is a set of statements postulated without proof and assumed to be valid. Every theory needs such a starting point, which will always remain without a proof. Therefore, a theory can never be considered as completely proven. From these axioms, then conclusions are drawn, which, if they refer to nature, can be confirmed in physical experiments. In Newton's case, the axioms serve to establish classical mechanics and thus form a foundation of theories based on it. From these axioms, a law of gravity could be postulated, which predicted the planetary motion in our solar system and was confirmed by astronomical observations. Is the theory proven then? Not at all. It has only been shown that the conclusions we get from the theory are consistent with our observations. However, it is quite possible that a theory may or may not make predictions that we cannot measure in experiments. In the case of Newton's law of gravity, this is exactly the case. If we observe the planet Mercury, which is closest to the Sun, more closely, we notice that its perihelion is rotating. According to Newton's laws, planets move on elliptical orbits, and the point closest to the Sun is called perihelion. A rotation of the perihelion, which results in the planets moving in rosette orbits, can be explained in part by Newton's theory of gravity, given the influence of the other planets. However, Mercury's perihelion rotates farther than predicted by calculations taking into account all known influences by celestial bodies. Therefore, it was initially assumed that there is an hitherto unknown planet called Vulcan, which is responsible for this deviation. However, this planet could not be detected even after intensive research. To explain this deviation from Newton's theory, a theory had to be found that incorporated Newton's laws but extended them so that the perihelion rotation could be explained by it. In addition, it should make further predictions which can be confirmed then experimentally. Albert Einstein succeeded in 1915 with his general relativity theory to find this extension. According to this, space, or space-time, is curved and planets move on the geodesics which describe the shortest distance between 2 points in a curved space. From this one can derive the elliptical planetary orbits as well as the perihelion notation and other previously unknown effects. Fundamental and effective theories. It should be noted, however, that this does not make Newton's theory of gravity wrong. It is, as the physicist says, merely not valid on all energy scales. What does this mean? This means that the Newtonian theory of gravitation is valid only in a certain range to describe the nature. For example, this theory is able to describe the gravitation that we experience every day here on Earth, and with a few exceptions, all gravitational effects that take place in our solar system. But if one comes to higher energies, it is to higher gravitational forces, e.g., in the environment of a black hole, the Newtonian theory of gravity loses its validity and must be replaced by the general theory of relativity. Moreover, at the atomic level, the gravitational force becomes so small that it becomes negligible compared to other forces, e.g. the electromagnetic force. Also, general relativity cannot be made into a quantum field theory, which are the theories we use to describe physics at a subatomic level. Therefore, we have not yet succeeded in describing gravity at this energy scale, and many physicists are still searching for a theory of quantum gravity today. Theories that are not valid at all energy scales are called effective theories, while a theory that is valid at all energy scales is a fundamental theory. So far, we have been able to find only effective theories in physics. One candidate for a fundamental theory is string theory, but it seems to be far from experimental confirmation. General relativity and Newton's theory of gravity are both effective theories and differ fundamentally in their interpretation. Therefore, it can be assumed that a fundamental theory will provide an interpretation that will be completely different from the previous theories while containing them within their respective energy range. Thus, it also becomes clear that while the effective theories are often able to accurately describe measurements at a particular energy scale, their interpretation is thereby not beyond question. In the case of fundamental theories, one assumes that their interpretation is correct because it makes the correct prediction at all energy scales. However, it is not at all out of question that there could be several fundamental theories with different interpretations, which all make the correct predictions on all energy scales and differ fundamentally in their interpretations. From this, one can see the limitations that scientific theories have. Even if they are able to predict and describe everything we can measure, they can never be proven, especially the interpretation of a theory is by no means beyond doubt. In summary, theories describe and explain facts based on certain assumptions that are accepted without proof. In particular, a theory is characterized by making predictions that can not only explain what we already know, but also make predictions about things we don't yet know that we can use to test that theory. This is all very theoretical, and I will try to illustrate this in the following. This was the audio sample of the first chapter, and we will listen to the second chapter, but first we will take a short break. I hope you like this first part of the episode. Please don't forget to give me feedback on what you thought of this episode. You can do this directly in Spotify if you are listening on Spotify, or you visit my website sci-faith.de/en, and there you can choose the contact form to give me feedback on the podcast, on Sci-Faith, on the other content, as you like. So it's not only Sci-Faith that is coming out as a book in English, but also my new novel that I'm currently still editing will be coming out in English soon too. So I hope this will be at the end of the year that I can publish it. It will be also only as an ebook, but at first at least. But I will keep you posted on the news there. So if you want to already know the title, currently the running title is Alien Thoughts, and it is a really interesting science fiction novel, and I really hope you will get it and enjoy it. So, but I will announce it once it's out, and probably there will be also an audio sample like this one to the novel once I'm done with it. Also, if you want to know more about According to Sci-Faith or the content that I produce, I encourage you to subscribe to my Substack, scifaith.substack.com, I believe it is. So just go there and you can subscribe to my posts, and then you will be updated about what's happening on Sci-Faith. You will receive all the new posts, blog posts that I'm either translating from German to English or that I'm directly writing in English. And also, if you want to know more about what's up, so regularly I'm posting on Twitter. Also there I will mostly be posting in English, so especially for if you're an English listener, this should be interesting. And there I will soon start to publish book reviews. So since I'm also doing a lot of reading and I'm always looking into books from this perspective of faith and from also a sci-faith perspective, or in this kind of way, it should be really interesting. So, and I will share my thoughts or my impressions of this in these Twitter threads. So if you are interested in that, then please follow me on Twitter. And so those are the ways you can reach me. You can reach me, as I said, by the contact form, and also on my website you can also find out more about Sci-Faith, about the book, and find all the other content I have yet produced. So with that, we are finished, or we are set to continue to the next part of this episode. Enjoy. Chapter 2. Theories are like children's riddles. We do not know what the rules of the game are. All we are allowed to do is to watch the playing. Of course, if we watch long enough, we may eventually catch on a few of the rules. Richard Feynman. As a kid, I loved solving kids' riddles. One of my favorites were the riddles in which various dots were given, each one with a number attached to it. The task was to connect these dots, starting with 1 and ending at the last number. Usually, to complete the circle, the last number was connected back to the first. If all numbers were connected correctly, a picture was formed. Before the numbers were connected, it was a mere accumulation of dots that did not indicate any pattern. However, by connecting the dots in the correct way, the picture underlying the riddle emerged. Scientists solve basically the same puzzle, except that the difficulty has been increased a bit. As a scientist, you have only given the individual points. The numbers that indicate the order in which the dots must be connected to get the underlying image are unknown. Moreover, one usually does not even know all the dots, but only a part of them. So imagine you have such a puzzle in front of you, only without the numbers. For the sake of simplicity, let's first take a game in which all the points are known. How do you solve this game? Many would probably start simple and try to find a solution by trial and error, which is not the worst approach and may well get results. Another option is to look at the dots and try to guess or deduce the underlying pattern through abstract thinking. Whichever approach one takes, it should become clear that it is theoretically possible to find a pattern that connects all the dots and makes a nice picture, but is still not the underlying picture. In other words, it may be that by connecting the dots you draw an elephant, for example, but the underlying image is a lion. Depending on the location of the dots, such an ambiguity may be present in these puzzles. If we extend this game and add that, as mentioned earlier, not all the dots are known, and as the dots are connected, additional dots may appear, now it can happen that certain images that were figured out are nullified by one of the new dots, and new images that did not seem possible before have now become possible. Also, ambiguities can occur in such a game and can be reduced but also increased by new points appearing. Additionally, in such a game, one can guess images that have places where there are supposedly no dots, but later some might appear. Now, what does this have to do with science? The dots describe measurements that have already been made. Newly appearing points are measurements that will be performed in the future. Connecting these points to form a picture is what we call a scientific theory. Thus, through new measurements, new points can appear that are not described by the old theories and therefore invalidate these pictures. On the other hand, new theories can assume points where there is nothing yet. If these are then measured later, this confirms the made assumption. It thus becomes clear that there can be ambiguities even in scientific theories. Thus, there can be several pictures which connect all points and yet look different. In scientific theories, these differences can be on the one hand differences in the description of the theory, and on the other hand difference in the interpretation of the theory. Sometimes these can be related. In the following, we will use the example of quantum mechanics to illustrate how this looks specifically in science. Different equivalent descriptions. Quantum mechanics describes physics at the atomic and subatomic level. It is one of the most successful theories of the last century. Successful in this sense means that all predictions of quantum mechanics could be confirmed experimentally. In other words, all the points that quantum mechanics had connected have emerged or were previously known. Quantum mechanics was first formulated in the 1920s by Werner Heisenberg and Erwin Schrödinger. Both already had different views of quantum mechanics, which are known today as the Heisenberg and Schrödinger pictures, respectively. In quantum mechanics, whenever a system has multiple states it can be in, these can differ in energy or other physical quantities. It is the case that as long as no measurement has been made, the states will be in superposition. This means that it is not possible to say in which state the system is before the measurements. Therefore, all possible states must be considered in the calculations. Often this is formulated in such a way that the system is, so to speak, in all states at the same time, which is not completely correct. Only when a measurement is carried out, the state in which the system is determined. Before a measurement is made, and also after the measurement is made, one can therefore only give probabilities that the system will be measured in a certain state. Mathematically, this behavior is described by so-called operators acting on the states. The states are described as vectors in a so-called Hilbert space. For each physical quantity, there is a separate operator. For example, the Hamilton operator is the operator for energy. If one applies this operator to a state, one receives the energy of the respective state. This behavior describes mathematically exactly the facts described before. The operators are the mathematical version of a measuring device for the respective observable, and the vectors in Hilbert space are the respective physical states. Thus, it is possible to describe quantum mechanics by this formalism using the mathematical subfield of linear algebra. In these considerations, however, we have disregarded how the system develops over the course of time, and above all, how this can be described mathematically. There are several possibilities for this. Either one considers the states as time-dependent or the operators. Both differ only in the mathematical structure but yield the same theoretical predictions. Therefore, it is possible that one can find a mathematical transformation that transitions from one picture to the other, making both pictures equivalent. The first variant is called the Schrödinger picture, and the latter is called the Heisenberg picture. Moreover, there is also the interaction picture, respectively the Dirac picture, which is a mixture of these two. In his doctoral thesis, Richard Feynman, at the end of the 1940s, put forward another formulation of quantum mechanics, which was also equivalent to the other formulations but far more descriptive. This is the so-called path-integral formulation of quantum mechanics. In classical physics, that is the physics we are familiar with, it is such that a system always tries to minimize the energy it requires. The equations of motions of a system, that is the path along which the object of the system move, can therefore be calculated by minimizing the energy to be expended. Although in quantum mechanics a system is also concerned with minimizing the energy, Heisenberg's uncertainty principle enforces that there must be fluctuations in the range around the minimum energy. If this were not the case, position and momentum, classical momentum is a mass times velocity, of a particle would be known at any time, which the Heisenberg uncertainty principle forbids. The path integral formalism now states that in contrast to classical physics, a particle does not take the path that requires the least energy, but all possible paths that a particle can choose from A to B must be summed up and weighted. From this sum, one then obtains the probability that a particle will travel from A to B. Also with this formalism, which is so different in its description, one can show that it is equivalent to the Schrödinger and Heisenberg picture. Here, too, one can derive the one formalism from the other. This illustrates that there are different representations of a theory, but they are equivalent to each other. Different interpretations. The other way to obtain different pictures would be via different interpretations. Again, this can be well illustrated in quantum mechanics. In classical physics, if the initial condition of a system are not known, it is possible to completely determine the future and past of the system. If I know what the speed of a meteorite is moving, at what speed a meteorite is moving and in what direction, and I also know its mass and other relevant data, I can calculate whether or not it will hit the Earth. Thus, in classical physics, everything is determined by its initial conditions. Therefore, classical physics is also called deterministic. In quantum mechanics, however, this is different. Whether a particle moves from A to B can no longer be predicted. One can only state a probability that this will happen. Quantum mechanics is thus indeterministic. This provides scope for various interpretations. The most common is the Copenhagen interpretation. It states that the random behavior of quantum mechanics does not indicate that there is a deeper reality not accessible to us in which this system is determined, but that it is a basic property of nature. While this interpretation is accepted by most scientists, it is mainly because it explains according to the principle of that's just the way it is, and because our knowledge of quantum mechanics does not expand no matter what interpretation we have for it. However, I personally can imagine that the probability character of quantum mechanics is indeed anchored in nature, and therefore I am most convinced by this interpretation. However, many people do not like this indeterministic worldview, which is why other interpretations have been developed. Albert Einstein had problems with this interpretation and was a supporter of theories with hidden variables. In these theories, it is assumed that there are other variables that describe the quantum mechanical system, but that cannot be measured. These variables determine the system. This is one of the few interpretations that could be experimentally verified and is now widely considered to be refuted. Another interpretation that has become very popular is the many worlds theory. Here one assumes that a particle goes from A to B, just not in every world. So here one assumes that a particle always goes from A to B, just not in every world. According to this, for every option a particle can choose, a new world is created in which the particle had chosen exactly this option. Probably this theory became so popular because it allows the conclusion that in one of these parallel worlds, one is a wealthy, world-famous philanthropist who has everything that one can wish for. But if you take a closer look at this theory, I think it very quickly becomes absurd. Because such a process in which a particle has several options to choose from happens uncountably often per second. If now in every second countless new worlds are created, and in every of these worlds countless new worlds are created, permanently lots of new worlds are formed which hardly differ from each other in most cases. Because if at the other end of the Milky Way a particle flies to the right instead of to the left, this has little influence on me and the whole mankind, but it will lead to an own world even if nothing significant should change relative to our world. Of course, this can be the case nevertheless, since there is actually no maximum number of worlds which should exist, at least we don't know of one. However, it seems to me personally extremely absurd. Even if some interpretations seem more reasonable than others, which is mostly subjective, no interpretation can be scientifically excluded as long as it does not contradict their observations. This is, as already noted, also the case for all alternative theories, except theories with hidden variables. Although theories with hidden variables can also be adjusted to be consistent with measurements. I hope I have been able to clarify for you in this chapter how scientific theories work. This possible ambiguity in the choice of theories is similar to a principle that also occurs in our scientific theories, the gauge freedom of theories. In the following chapter, or in the next chapter, I would like to explain and discuss this. So this next chapter will not be part of this audio sample, and to know more about this you would have to get the book once it's out. So I hope you enjoyed this episode. I hope you enjoyed this short sample about of my new book. You might have realized there were some places where I needed to stop for a bit or where I need to read twice. So it's not like an audio book. It's not that kind of a quality, but I think it gives you a small insight in what my book is about, what I'm talking about. I will dive deeper into this topic about the different ways to interpret the theory, but I will also go further and look at faith, look how we can be able to be convinced that our faith is true, and many more things. And I also look how to look at science from a faith perspective, which has also come up very often in this podcast. So I hope you are excited about it, and as soon as the book is out, I will tell you more about it, where you can get it. So most likely it will only be published at first as an ebook, but if you have a Kindle or some other device to read it on, then I would be glad if if you get it, and I will tell you as soon as it is available. So thank you for listening to the According to Sci-Faith podcast, and we'll see you next time.